All right, now we are looking at solving exponential equations using logarithms. So previously when we were solving for the exponent in an exponential equation, we only had the options of getting common bases if possible. And some of the work that you've done not very long ago in this unit required you to go back to understanding how this works. So 81 could be expressed as a base of 3. It's 3 to the exponent of 4. And then the only way that these equal each other is if x plus 2 is equal to 4. And then subtract 2 from both sides, and we get x is equal to 2. Okay, so that is one method that we had learned. But if we couldn't get the bases the same, then we just had a guess and check method. So for example, if we had 5 to the x was equal to 23, we know that 5 to the 1 is 5, 5 squared is 25, so we know that x is pretty close to 2, but a little bit less than 2, and then we would try like 1.9 and 1.8, and then we would narrow that down to see what gets closest, depending on how many decimal places we need to go. Also, another way to solve that if we couldn't get common bases was to use Desmos to solve this. So we would potentially graph y equals 5 to the x, and then we would graph y equals 23, and then we would see where those two graphs intersect each other, and then that would give us the x coordinate of the intersection point, and the x would be the solution to the equation. So now we're going to learn how our log laws can help us solve for that exponent. So here's my example here. First of all, 5 to the x is equal to 30. Now we know that as long as we do the same thing to both sides of the equation, it stays equal. So here's what we do. We take the common logarithm, because that's the button we have on our calculator. We take the common logarithm of both sides. So we're going to do the log of this side and the log of the other side. Okay, now in doing that, that allows us to apply the power law of logs. So this x will come down front, and we'll end up with x times the log of 5. So x times the log of 5 would equal the log of 30. Now the log of 5, I can evaluate that. That's just a number. I can put that in my calculator and figure out what that number is. It's a decimal number, but that's okay. It's still a number. So to get x by itself, it's being multiplied by that number, whatever the log 5 evaluates to. So we can divide both sides by the log of 5. So our x then will equal the log of 30. So this is the common logarithm. This has a base of 10 divided by the log of 5. Now that's how we can put this into our calculator and get the answer to it. So put the log of 30 in your calculator, divide that by the log of 5, and we'll just take that to a couple of decimal places. So log of 30 divided by the log of 5, and that gives us about 2.11. So leaving it in this form, this is the exact form of the answer. So this is the exact answer. Exact. Oh my goodness, I'm having trouble writing with this thing tonight. Let's try that again. So this is the exact answer, and this is the 2.11 would be the decimal approximation. All right, so it depends if you want an exact answer or not. All right, so that's easy enough. Try the next one. Take the common log of both sides. We're going to have the log of 9 to the x minus 5, and that will be equal to the log, common log, of 123. Apply the product law of logs, and that's going to equal x minus 5 times the log of 9. All right, now log of 9 is just a constant. It's just a number, so we can divide both sides by the log of 9. Divide by the log of 9. And then what we have here, let me just move that up so we can work with it. Divide by the log of 9. We're going to be left with an x minus 5 is equal to this exact value, whatever the log of 123 divided by the log of 9 works out to be. And then we could add 5 to both sides, and our x will equal whatever that works out to be. Okay, so I'll just leave it in its exact form there. You could take it to a decimal if that makes you happier, more comfortable, but if you're going on to advanced functions, you should get comfortable with working with exact values. All right, part C. Now, before we can take the common log of both sides, I mean, we could at this point, but then we have to apply the product law backwards. What I'm going to do actually first is get it so I just have one base and one exponent on the left side of the equal sign. So I'm going to divide out, the 3 is multiplying it, I'm going to divide both sides by 3, divide that 3 away from there. So that leaves us with just 6 to the exponent x plus 2. My eyes are getting tired. 90 divided by 3, that would be 30. And then we could common log both sides. Take the common log of both sides, we get the log of 6 to the exponent x plus 2. That's going to equal the common log of 30. And then again, power law of logs, I'm going to have that x plus 2 comes down front. Make sure that's in brackets because that's all of the exponents, so that whole thing is multiplying the log of 6. That's equal to the log of 30. Divide both sides by the log of 6. And then from there, we would have x plus 2 equaling that log of 30 divided by the log of 6. And then we could subtract 2 from both sides, so we get x being equal to the log of 30 divided by the log of 6, and then subtract 2. All right, last example. Now this actually is similar to the question we had at the very beginning of the logarithmic unit. We were trying to figure out when will the population of Edenville double. Similar question, different numbers of course, and we're actually working with exponential decay instead of growth, but same process here. The first step, I would try and isolate my power by dividing both sides by 35,000 here. And when I do, I can reduce that, take 3 zeros off that, 3 zeros off of that. That gives me 20 over 35. Both of those are divisible by 5 as well, which would make that a 4/7. So 4 over 7 would be equal to 0.87 to the exponent x. Common log both sides. The x is going to come down front. So we would have x times that log of 0.87, and that's equal to the log of 4/7. And then divide both sides by the log of 0.87. Okay, so that will give you the exact answer there. You can take that to a decimal place if that would make you smile, make you happier. I know some of us are more comfortable with that. So that kind of brings us to another log law that I want to talk about here very briefly. Log of 0.87. Okay, so at the bottom of this page, which I'm out of room because I write a lot bigger on this iPad, but you might hopefully have some room here. If I started with something that looks like this, the log, I know we did a question where we had, let's put the base of 2, and let's say we had the number 40 here. So 40 I can't express as a power of 2, but if I wanted to actually, I want to know what that's equal to. So I'm going to say that's equal to x. Okay, that's equal to x. So really what we're saying is 2 to the exponent x, I'm writing this in exponential form here, is equal to 40. If I common log both sides of that, take the log of that side and the log, I'm going to squeeze that in here, of this side, I apply that power law of logs. That's going to make that x times the log of 2 equals the log of 40. Then that means my x is going to equal the log of 40 divided by the log of 2. So for those of you who have the fancy buttons on your calculator, we don't actually have to have those fancy buttons. Anytime you want to do the log of x with a base of a, we'll call it base of b, the answer you're going to get is just taking the log of the argument. So let me highlight in yellow here, the log of the argument divided by the log of the base. The log of the base. So that will always be true. So let me just write that in general terms here. If you have the log of x with a base of b, that is always going to equal the log of the x with a common log of 10 divided by, so common base, the base is 10, the common log of the base. So that's another little rule you can add to a summary sheet if you're creating a summary sheet for this unit.